Okay. I want to start today with a really uncomfortable contradiction. It's one of those things that just makes you sit back and realize how messy, how interconnected everything actually is.
Hmm.
Imagine we finally do the right thing. We pass this huge global regulation to clean up the air, remove toxic sludge from the sky and save potentially tens of thousands of lives.
It sounds like an absolute victory, doesn't it? A complete no-brainer.
Exactly, the kind of headline everybody cheers for. But, and here's where it gets complicated. What if I told you that by cleaning up the air, we might have accidentally cooked one of the most precious ecosystems on the planet?
It sounds like the plot of some dark sci-fi novel.
Uh-huh.
The idea that a solution to one crisis could actually accelerate another. But that is exactly the tension we're looking at today.
We're talking about the Great Barrier Reef. And more specifically, we're going to be looking at how a rule change for shipping fuel back in 2020 might have unintentionally just ripped away this massive invisible sunshield over the ocean.
It is a classic, just tragic case of unintended consequences. And we have a fascinating study to unpack for this. It's titled, Ship Fuel Sulfur Content Regulations May Exacerbate Mass Coral Bleaching Events on the Great Barrier Reef.
Catchy. I'm sure that flies off the shelves.
It's a bit of a mouthful, I'll admit. But the science inside is incredibly tight. It was published in January 2026, so it's very fresh, by Robert Ryan and his team in Communications, Earth, and Environment.
Which is a nature journal, so it's top-tier stuff.
Absolutely.
So the mission for this deep dive seems pretty clear then. We need to understand the physics of how cleaning up ship exhaust, which sounds, objectively good, ended up letting a huge extra dose of solar radiation just slam into the reef.
Right, when it was most vulnerable.
Mhm.
And to do that, we have to look at the atmosphere, the shipping industry, and the biology of the coral itself. It's a complex web.
So let's start with the culprit, or I guess the former hero, the pollution itself. I think
Yeah.
most people, myself included, just imagine ship exhaust as this black, sooty smoke that's bad for everything.
Right, it looks bad, smells bad.
But the source material suggests it was doing something else entirely up there.
That's right. To understand this, you have to get what merchant ships have been burning for decades. They ran on heavy fuel oil.
The bottom of the barrel stuff.
Literally. It's the sludge that's left over after you refine everything else. The gasoline, the jet fuel. It's thick, it's cheap, and it is full of sulfur. And when you burn it, you pump huge amounts of sulfur dioxide, or SO2, into the atmosphere.
And that SO2 is the key here.
It is. When it hits the air, it goes through some chemical reactions and turns into sulfate aerosols. These are tiny microscopic particles. And in terms of climate, they are surprisingly powerful.
Okay, so what do they do?
They do two things to sunlight. First, you've got the direct effect.
Which is just blocking the sun.
Basically, yeah, the particles act like millions of tiny mirrors. They scatter incoming sunlight back into space before it ever hits the ocean. It creates a haze.
So it's like putting a pair of sunglasses on the planet.
Exactly.
Yeah.
We've been looking at the ocean through a pair of dirty, sulfur-tinted sunglasses for half a century.
That makes sense. But then there's the indirect effect, which the notes say is often even more powerful. And this gets into cloud physics.
My favorite. This is where we talk about cloud condensation nuclei, or CCN.
Okay, let's break that down. Cloud condensation nuclei.
Think of it this way. Clouds don't just happen. Water vapor, which is invisible, it needs a surface to condense onto, to form a droplet. It needs a little seed,
And that seed can be a speck of dust, a grain of salt.
or a particle of sulfate pollution from a ship.
So the pollution gives the water vapor a place to grab onto.
Precisely. Now imagine two scenarios. Scenario A, clean air over the ocean. Not many particles. The water condenses onto the few available specks, making fewer but bigger droplets.
Okay.
Scenario B, you pump ship exhaust into that same air. Suddenly you have billions of extra seeds. The water vapor divides itself across all those billions of particles. You get a cloud made of many, many tiny little droplets.
So the water gets spread out more thinly.
Exactly. And here's the physics kicker. A cloud made of many tiny droplets is whiter. It's brighter.
It reflects more light back to space.
Yes, this is called the Toomey effect. It gives the cloud a higher albedo or reflectivity. It's the difference between a thin gray mist and a blindingly white, fluffy cloud. The pollution basically turbocharges the clouds to be a better sun shield.
So for decades, our shipping lanes have been accidentally deploying a giant parasol over the ocean. We were geoengineering without even knowing it.
That's a perfect way to put it. And then came 2020.
Right, the year everything changed, and we're not talking about the pandemic here, we're talking about the IMO.
The International Maritime Organization. On January 1st, 2020, they brought in a regulation called FSC 5. It was a monumental shift. They capped the sulfur content in ship fuel at 0.5%.
And before that it was what?
The global limit was 3.5%. So you're talking about slashing sulfur by nearly 85% overnight.
That is a massive drop. And did the shipping companies actually comply?
Surprisingly, compliance was very high. The study notes that around the Great Barrier Reef, this led to a 79% reduction in sulfur dioxide emissions and a 76% drop in those sulfate aerosols.
Wow. So practically overnight, the air got way, way cleaner.
Much cleaner. And we have
Yeah.
to pause and say, that is a good thing. For people in port cities like Brisbane or Townsville, this is a massive public health victory.
Sure, we're not rooting for sulfur here. We don't want acid rain or asthma.
No, but for the reef, specifically for the energy balance of the reef.
We ripped the sunglasses off.
We ripped off the sunglasses
Yeah.
and we folded up the parasol, which brings us to the core of this study, the demasking event.
Demasking, that sounds ominous.
It is. The pollution was masking the true heat from the sun. Now the mask is off. And the researchers zoomed in on a very specific tragic period, February 2022.
I remember that. That was a bad bleaching year.
It was. But it was weird. Scientifically, it was an anomaly because 2022 was a La Nina year.
And for anyone who doesn't follow the ENSO cycles, La Nina is usually the cool one for Australia, right?
Correct. El Nino is hot and dry. La Nina is usually cooler, wetter. It's supposed to be when the reef gets a break. But in 2022, despite those conditions, 91% of the surveyed reefs suffered bleaching.
That shouldn't happen. It's like getting a sunburn in winter.
Exactly. So the researchers asked, did the lack of ship pollution play a role? Did the IMO 2020 rule tip the scales?
How do you even prove that? You can't run 2022 over again with dirty ships.
Well, in the world of atmospheric modeling, you actually can. They used a model called WRF Chem. It's basically a what-if machine. They simulated the weather of February 2022 in 3 parallel universes.
I love when they do this. Okay, what were the 3 universes?
Universe 1 is reality, ships with the new, clean fuel. Universe 2 is the counterfactual, ships still burning the old, dirty, high-sulfur fuel. And Universe 3, as a baseline, is no ships at all.
So when they compared our world, the clean fuel world, to the dirty fuel world, what did they see?
A huge demasking effect. By cleaning the fuel, we allowed a lot more solar energy to hit the water. During the daytime, the reef got an extra, get this, an extra 11 watts per square meter of solar radiation.
11 watts per square meter. Let's pause on that. In the grand scheme of things, is that a big number?
It is enormous. To put it in perspective, the total energy imbalance from all our greenhouse gases, the CO2 trapping heat, is maybe 1 or 2 watts per square meter on a global average.
And this was 11.
11. Localized, concentrated, right on a reef during the day. It's like turning a dimmer switch way, way up.
And was this because of the clouds changing, like we discussed?
That was one of the big surprises in the study, actually. We spent all that time on the cloud brightening effect. But in this specific case, the model showed that the direct effect was the dominant factor.
So it wasn't about making clouds fluffier?
No.
Huh.
The air was just so much clearer that sunlight was punching right through. The haze that usually scatters some of that light was simply gone.
But there's another layer here, right? The study mentions this effect isn't constant. It depends on the weather, on the wind.
This is a crucial nuance. It's not just about the ships, it's about the wind. They compared February 2022 to February 2023.
Okay.
In 2023, the region had strong southeasterly trade winds.
The classic gusty winds.
Right. And when those winds are blowing hard, they act like a leaf blower. They just blow the ship exhaust away, clean or dirty. It doesn't have time to accumulate.
So if it's windy, the pollution doesn't matter much either way.
Exactly. But February 2022 was different. We saw doldrum conditions, light northerly winds, stagnant air.
The air just sits there.
It just sits there. Now picture the old days, pre-2020. With stagnant air, the sulfur from the ships would have just built up. It would have created this thick, hazy smog layer right over the water.
A strong shield right when the sun is hottest and the air is still.
Precisely. But in 2022, with clean fuel, the air was stagnant, but there was no sulfur to build up. The haze never formed.
I see the bitter irony. The weather conditions that cause the worst heating, hot, still days are exactly when the pollution used to help the most.
You've hit the nail on the head. The regulation's negative impact is maximized exactly when the reef is most vulnerable.
So let's connect this to the coral itself. We have this extra energy, these 11 watts. What does that actually do to the temperature of the water?
The study translates that energy into sea surface temperature, or SST. They calculate that the clean shipping rules cause the water to be between zero point zero 0.05 and 0.15 degrees Celsius warmer.
Okay, I have to play devil's advocate here. 0.15 degrees, that sounds tiny. I mean, my coffee cools by more than that, and I don't notice. Why does that matter to a massive reef?
It's a totally fair question. And in isolation, it is tiny. But you have to view it through the lens of biological thresholds. Have you heard of degree heating weeks?
DHW, it's how they measure cumulative heat stress on coral, right?
Yes. Think of the coral as a camel carrying a heavy load. The background, global warming, the El Nino cycles, that's the main cargo. The camel is already trembling, its knees are buckling, it's right at its breaking point.
Barely holding on.
Exactly. And that extra 0.15 degrees from the shipping regulation, that's the straw that breaks the camel's back. The study suggests it added about 5 to 10% additional thermal stress.
10% isn't nothing.
When you are hovering right at the mortality threshold, 10% is everything. It's the difference between a coral bleaching and recovering, or bleaching and dying.
So it made that bleaching danger zone more likely to happen.
10% more likely, according to their work. It's just tragic. We cleaned the air, and in doing so, we might have pushed the coral over the edge.
It brings up a concept from climate science, right? Termination shock.
Yes, usually we talk about that with, sci-fi geoengineering ideas. Like if we put giant mirrors in space and then suddenly took them away, the temperature would spike catastrophically.
Well, we did it here by accident.
We performed an unintentional geoengineering termination shock. We were cooling the oceans with ship exhaust for 50 years, and then on January 1st, 2020, we just turned the machine off.
Which leads to the now what part of this. Because the study doesn't just point out the problem, it actually gestures towards a solution, a way to get the shield back without the pollution.
It does. And it circles back to clouds. We talked about marine cloud brightening, or MCB. This is an idea where ships would spray microscopic seawater droplets into the air.
Just salt water, not chemicals.
Just salt water.
Yeah.
But billions of tiny salt crystals.
So instead of sulfur acting as the cloud condensation nuclei, you'd use natural sea salt.
Exactly. The salt acts as the seed. It brightens the clouds, using that same Toomey effect, but without any of the acid rain or health hazards.
And the study suggests this could actually work for the reef.
It gives us a really crucial insight. Remember the Goldilocks weather? The doldrums?
The stagnant days when the heat is worse.
Yes. The study suggests that MCB would be most effective during those exact same conditions. When the wind dies down, that's when you need to go out and brighten the clouds.
So it's not a global 204/7 project. It sounds more surgical.
That's the key. You might only need to do it on certain days in certain areas when the conditions are just right for a heat wave.
And we already have the ships in the right place.
That's the ships of opportunity idea. There's a major shipping lane running right up the coast from Brisbane. The study shows pollution from those lanes used to drift over the reef if you equip those same ships to spray sea salt.
You could replicate the cooling effect we lost, but do it cleanly.
Theoretically, yes. You turn the problem into the solution.
Before we wrap, I want to zoom out. This was a global rule change. Is the whole world heating up a little bit because of this?
To an extent, yes. The study notes that global estimates for the warming effect range up to 200 milliwatts per square meter. There's a lot of debate right now about how much the recent spike in global temperatures was driven by this rule change.
But let me get the scale right. You said the global effect was maybe 200 milliwatts?
Right, 0.2 watts.
But on the reef, it was 11 watts.
Exactly, and that is the key takeaway. The reef sits right next to a major shipping corridor, so the localized effect is just intense. It shows how local pollution can have a massive impact on the local climate.
It's a sobering thought. You change a fuel mix in an engine, and a coral colony hundreds of miles away bleaches.
It just destroys the idea that we can solve these problems in silos. You can't have an air quality department and an ocean health department that don't talk to each other. When you tug on one string, the whole web moves.
So where does this leave us? We obviously can't go back to burning dirty fuel.
No, absolutely not. The health benefits are real and necessary. We can't go backwards. But we have to acknowledge the trade-off. We traded cleaner air for a warmer ocean, and now that we've removed that cooling buffer, the urgency to cut greenhouse gases is even higher. We've lost our accidental safety net.
It's a paradox. Clean air is good, but clean air also reveals the true extent of the heating we've caused.
That's the scary part. The pollution was hiding some of the damage. Now the mask is off.
I want to leave our listener with a thought that came up for me reading this. We've spent decades arguing about whether we should start geoengineering the planet, whether it's playing God.
It's one of the biggest ethical debates in science.
But this study proves we've already been doing it. We were geoengineering the planet with sulfur for 50 years. We just stopped. So the question isn't, should we start manipulating the climate? The question is, do we have an obligation to start doing it intentionally and safely now that we've stopped doing it accidentally and destructively?
That is the question. If we broke the unintentional cooling system, do we owe it to the reef to build an intentional one?
Something to think about. Thanks for joining us on this deep dive.
A pleasure, as always.
Keep looking for those hidden connections, everyone. We'll see you next time.